My name is Olivia.
And my name is Emily.
And we are in a bioelectronics class. Given a project to explain a biosignal, we have chosen electrooculography, and we're going to dive into what that is and how it can be used.
Over the past century, eye tracker machines utilizing the study of eye activity and eye movements have evolved greatly and provide a tremendous amount of information regarding emotional states, psychiatric disorders, physiological behaviors, perception, desires, and needs. Beyond providing information, this signal can then be used to serve as an input for computer interface systems for those who are unable to use a mouse or a keyboard for means of communication, or a controlling mechanism for those who are unable to operate a wheelchair. Electrooculography is the technique used to measure the electrical potential between electrodes placed on the skin that obtains signals from eye movement. The result is called an electrooculogram.
Electrooculograms can be recorded through vertical or horizontal eye movement. Later in this video, we will be observing a circuit that takes in an electrooculogram, and it will be using horizontal for reference. Electrooculograms can be An electrooculogram, or EOG for short, ranges from 0.05 to 3.5 millivolts in humans, and that voltage difference is proportional to eye displacement. Eye movements are controlled by 6 muscles in each eye, and electrooculograms were first researched in 1951, with clinical applications beginning in 1962. The uses of signal obtained from EOG is not limited in its use to improve technology and quality of life of disabled.
The human eye is an electrical dipole with a negative pole at the retina and a positive pole at the cornea. A leftward gaze results in a negative change in potential difference, and a right gaze results in a positive change in voltage difference. The human eye The circuit shown here is a single-channel EOG acquisition circuit that is used to capture and analyze horizontal eye movement. The different components of the EOG circuit are labeled for their purpose. The circuit shown here
The input for this circuit comes from 3 different electrodes placed on the face of the participant, 2 of which are for differential amplification and 1 for reference. At the beginning of the circuit, the instrumentation amplifier is used to reject the majority of common mode signals. It must have a high input impedance in order to minimize signals being lost at the skin electrode contact. This component must have high CMRR, or common mode rejection ratio. This will reject noise from the input of the signal. In order to further reduce noise, a low-pass filter was added at the inputs to suppress the effect of high-frequency noise. Additionally, 2 Schottky diodes in the driven right leg were added to protect the user from electrostatic discharges and over-voltage peaks, which could be very dangerous. Next, the signal was amplified to get maximum gain before continuing to get filtered. This was done by being put into a non-inverting operational amplifier.
Next, a sequence of high-pass filters were applied to the signal to remove noise from the EOG acquisition and remove any potential DC offset. It can be seen in the output graph of V2 that there is less noise than the output graph in V1. Another non-inverting amplifier was used to add gain to the filtered signal, which has a variable gain range from 60 to 460 volts per volt. The second op-amp was used to add a DC offset having a range from -5 volts to 5 volts. This is necessary because of the requirements of the analog to digital converter, which accepts only positive values up to 5 volts. Lastly, a series of low-pass filters were applied to filter out the unwanted high frequencies and provide substantial gain to the signal. The signal would then be inputted into an ADC, or analog to digital converter, where it can further be used for biomedical practices.
As briefly mentioned before, an electrooculogram can be used to provide access to someone who would otherwise be disabled. Here is an example of a computer interface system that can be controlled via the signal from an electrooculogram. The movements necessary from the eye to control certain motions in this computer interface system varies between a system, but is not difficult for a user to learn. This gives access to a computer to someone who would not otherwise be able to use a keyboard or a mouse.
Here is an electric wheelchair, which is the main area electrooculography is moving into.